Good day, everyone. So we are on the last week of the first quarter, and I'll be discussing logarithmic functions, which is the last type of function. So for our first lesson, it is all about representing real-life situations using logarithmic functions. And for this particular topic, here are the objectives. Define logarithmic functions, transform exponential functions to logarithmic functions and vice versa, evaluate logarithmic expression, represent real-life situations using logarithmic functions. So as we proceed, this is the definition of logarithmic function. So let a, b, and c be positive real numbers such that b is greater than 0 and b is not equal to 1. The logarithm of a to the base b is denoted by log a, b. So a here, and then b is the base, and is defined as c equals the logarithm of a to the base b if and only if a is equal to b raised to c. Okay? So this is our basic notation for the logarithmic. Okay, so here are examples where you can see an exponential equation being transformed to logarithmic form, okay? And vice versa, of course, where a logarithmic equation can be transformed to exponential form. So say we have the given exponential equation, 7 squared is equal to 49. So in logarithmic form, that is equal to the logarithm of 49 to the base 7 is equal to 2. So as you can see in the exponential equation, the power, which is 49, becomes the value of our a, the base, which is 7, becomes still the base in the logarithmic form, and 2, the exponent, becomes the value of the logarithm, okay? So transforming this one amount to exponential, then we'll have the base, and then this one becomes the exponent, and this is the value. Okay, so if we have 27 raised to 1/3 is equal to 3, then that is equal to 27, that is equal to, in terms of logarithmic form, the logarithm of 3 to the base 27 is equal to 1/3, okay? So in short, finding the cube root of 27, that is equal to 3. That's the value here, okay? The next, if we have the quantity m minus 2 raised to the third power is equal to x, then that is equal to the logarithm of x to the base m minus 2 is equal to 3. Okay? And then if we have e raised to x, okay, going back with the last example, e raised to x is equal to 3. So we have here the Napierian e. If we have that as our base, then the logarithmic form will be equal to ln, which is the same as the natural logarithm. Okay, so that is equal to ln 3 is equal to x. Okay, so how do we find the value of each logarithm? Say we have the logarithm of 64 to the base 2. Okay, so you can use actually your calculator. Okay, but in that sense, if we will try to rewrite this in terms of exponential form, since we are finding the value of x, then it can be written as 2 raised to what power? 2 raised to x is equal to 64. So what exponent must 2 be raised to equal to 64? So try to think of it, and that will be equal to x equals 6, right? Because if you will try to check, 2 raised to the 6th power is equal to 64. So I hope you get it with the first example. If you will use your calculator, you need to find the key, the logarithm with 2 boxes, where you can write there the base, which is 2, and then the value, which is 64. Okay, so, and then pressing equal sign, then you'll get the same, which is 64. Okay, so how about if you have the logarithm of 2 56 to the base 4. What's the value of that? Okay, and you're correct. If you will use the calculator or try to solve for it, that is equal to 4, because 4 raised to the raised to the fourth power is equal to 256. Okay, so that's a way of checking. Okay, how about if we have the logarithm of 32 to the base 1/2? And yes, you're correct. The value of that is -5, because 1/2 raised to -5 powers, remember in algebra, we cannot evaluate an expression having a negative exponent. So all we have to do is to find the reciprocal, or to reciprocate 1/2, and that is equal to 2, then raise that to the 5th power, making the power, once you reciprocate your base, your exponent will be positive already. So 2 raised to the 5th power is equal to 32. Okay? How about if we have the logarithm of 81 to the base 3? So to what exponent must 3 be raised so that its value will be equal to 81? And you're correct. That is equal to 4. Okay? Because 3 raised to the 4th power, 3 times 3 is 9, times 3 is 27, times 3 equals 81. Okay? Now, how about this one? What's the difference if we have this one? Okay, if you cannot see a base, automatic, it is equal to, the base is equal to 10. Okay, and what's the value of 1 over 1,000? The logarithm of 1 over 1,000. Okay, to what exponent must 10 be raised to equal to 1 over 1,000? Okay, and you're correct. That is equal to -3. Okay, so that's how we find the value of a logarithm. So I hope you were able to get, or how to evaluate a logarithmic function, or a logarithm rather. Okay, so as we continue, this one is a real life example of a logarithmic function. So a richer scale. Actually, this is used if we have an earthquake. Okay, so this is the formula. Richter scale is equal to 2/3 times the logarithm of E over 10 raised to 4.4, where E actually is in joules, which is the energy released by the earthquake. 10 raised to 4.4 joules is the energy released by a very small reference earthquake. So if we have this one, the Richter scale, you'll be able to find the earthquake. Okay, the magnitude actually. Okay, so let's have this one. Suppose an earthquake released approximately 10 raised to the 8 joules of energy. What is the magnitude on the Richter scale, and how much more energy does this earthquake release than the reference earthquake? So using the Richter scale, so since E given in the problem is equal to 10 raised to the 8 power, substituting that value in our formula will make the magnitude, or will be able to find the magnitude of the earthquake as approximately equal to 2.4. Okay, so the logarithm of 10 raised to 3.6. Why is it 3.6 already? Remember, if we have the same base, all we have to do is to subtract the exponents. 8 minus 4.4 is 3.6, and raising 10 raised to 3.6 and finding its logarithm multiplied by 2.3 is approximately equal to 2.4. Okay, and then the second question, the magnitude, the energy. Okay, remember this form is the energy of the earthquake, the E here. So if we will try to solve 10 raised to the 8 over divided by 10 raised to the 4.4 is equal to 10 raised to 3.6, and that is approximately equal to 3,981 times more energy than the reference earthquake. So this one is the energy released by that earthquake in reference to the original one. Okay, the second topic is all about identifying which is a logarithmic function, equation, and inequality. So this is almost the same as identifying exponential function, equations, and inequalities. So these are the objectives: distinguish logarithmic function, logarithmic equation, and logarithmic inequalities. Then apply basic properties of logarithm and laws of logarithms, and then solves logarithmic equations and inequalities. Okay. So basically, if we will define the logarithmic function, this is a function of the form f of x, or you can use y, is equal to the logarithm of x to the base b, such that b must be greater than 0 and must not be equal to 1. So these are the examples. As you can see, you can use f of x or y so that we'll have a logarithmic function. And then when it comes to logarithmic equation, of course, you have to take note of the equal sign. So it can be on both sides of the equation, must have or must contain logarithm or one side only. Okay. So it is an equation involving logarithm. Look at the first example where both sides of the equation contains logarithm. While on the second one, it's only on the left side. Okay, so both are examples of logarithmic equation. Then for the logarithmic inequality, as long as there is an inequality symbol, that it can be classified as logarithmic inequality. So again, it can be on one side only of the logarithmic inequality or on the two sides, okay? But with our two examples, it's only on one side of the equation that we have the logarithm. Okay, let's try to classify the given logarithm as to logarithmic function, logarithmic equation, and inequality. So the first one is given already. It's a logarithmic equation basically because of the equal sign, right? Let's have the second one. Okay, looking at the symbol, as long as we have the inequality symbol, then it can be classified as logarithmic inequality. The last one, we have the notation of f of x, which is our notation for function. Therefore, although it has an equal sign, but there is an f of x notation or a y on one side, then it is a logarithmic function. So that's the last one. How about this one? We have here the notation for the function, but look at the right side of the equation. It does not contain logarithm. Therefore, it's neither of them. Okay. So this is actually an example of an exponential function. I don't know if this is still the learning task number 3 in the WHLP, but if in case, you can do this as your exercises. But then again, ano po, just follow the WHLP uploaded in the GC or in the Google Classroom. Okay, let's have the next topic. Solving logarithmic equations and inequalities. Okay, so you have to consider the following properties and laws of logarithm in order for you to solve logarithmic equations and inequalities. As for our first property, if we have the logarithm of b to the base b, so if that is the same, automatic that is equal to 1. Okay, no need to solve for that. If we have the logarithm of 1 to the base b, that is automatic equal to 0. Okay, and then if we have the b raised to logarithm of x to the base b, so having the same base here and then the base of the logarithm, so that is equal to x. Okay, and then the fourth one, if we have the logarithm of b raised to the x power to the base b, that is equal to x. Actually, these two, ano pala, okay, it's different. Okay, so whatever is the exponent here becomes the value. This one naman, whatever is the x here becomes its value as long as the base and the base of the logarithm is the same. Then when it comes to the laws of logarithm, we have the product of the logarithm is equal to the sum of the two logarithms and vice versa. So if in case the given is the sum of the two logarithms, then it can be simplified as the product of the two logarithms. If we have the quotient of two logarithms, that is actually the same as finding its difference, or the difference of the two logarithms is equal to the quotient of m and n to the base b, as long as they have the same base, but if they do not have the same base, then you cannot simplify the quotient or the difference as to the other side. Okay, and then lastly, last law, if you have the logarithm of m to raise to the n power to the base b, that is actually equal to the exponent here. You have to bring down that. We have n times the logarithm of m to the base b. Okay, whenever the value here as an exponent, so you can put that in front. Okay, let's try to find the value of x. Given this one, the logarithm of x plus 8 to the base 5 is equal to 3. So the first thing that you have to do is to rewrite this as to exponential form, into its exponential form. And in doing that, remember the base, and then this one will be the exponent. So we'll have, yeah, so x plus 8 is equal to 5 raised to the third power, which is the equivalent in exponential form. And then solving 5 raised to the third is equal to 125. Then transpose 8 on the other side, then the value of x is equal to 117. Okay? Because it's 125 minus 8. That's why it's equal to 117. You can check that by substituting the value of x on the original one. So if you will do that, we'll have 117 plus 8 is equal to 125. Okay, so if you will evaluate 5 raised to the third power, that's the value of the 125 here. Okay, let's have the second example. Okay, the logarithm of x to the base 2 plus the logarithm of x minus 6 to the base 2 is equal to 4. So remember one of the laws, okay? If we have the sum and if they have the same base, we can actually simplify this as the product, okay, of the logarithm. Thus, in solving that, we need to combine this as product. So the logarithm of x times the x minus 6 here, having the same base as 2 is equal to 4. Okay? And then transforming that to its equivalent exponential equation, the base of quantity x, then distributing x inside the parentheses, we will have x's power, which is 16. So I tried to reverse them, but they will have the same sign. And then combining them into one side of the equation, then we will have x. Then let us try to factor this trinomial. Its factors are x minus 8, x plus 2 equals to 0. Then equate each factor to 0 to find the value of x. Then we will have x is equal to 8 and x is equal to negative 2. But remember the definition. Yeah. So this will be the two values. Right? But remember the definition of, okay, that's the base pala, sorry. So those are the two values of x. Okay. Now let us try to remember these properties of logarithmic inequality. Okay. So if you have given the logarithm of x to the base b, you need to consider if your b is greater than 1 or it's greater than 0 but less than 1, and then the x sub 1 and then the x sub 2. Okay? So if in case b is greater than 1, then x sub 1 is less than x sub 2 if and only if the logarithm of x sub 1 to the base b is less than the logarithm of x sub 2 to the base b. While if b is greater than 1 and x sub 1 is greater than x sub 2, then the case is that the logarithm of x sub 1 to the base b is greater than the logarithm of x sub 2 to the base b. If 1 is less than x sub 2, if and only if the logarithm of x sub 1 to the base b is greater than the logarithm of b to the logarithm of x sub 2 to the base b. So as you can see, if we will try to compare the first and the third, okay? So if in case it's greater than 0 but less than 1, the value of the two logarithms or the first logarithm becomes greater than the value of the second logarithm. Then the last case will be just the opposite naman of the second property. So it will be less than. So let's try solving the third example, which is an example of a logarithmic inequality. Right? So solving for the logarithm of x to the base 3 is less than 4, then, okay, so we have to ensure that the logarithm is defined. That is, if x is greater than 0. Okay? So in doing that, we have to make both sides equal to logarithm of 3 so that we can cancel both the logarithm. Okay? So logarithm of 3, a logarithm of x to the base 3 is less than the logarithm of 3 raised to 4 to the base 3, same base. So dropping out the logarithm, we have x is less than 3 raised to the 4th power. And as you can see, your b, which is the 3 here, is greater than 1. Therefore, we can really check that the logarithm on the left side is less than the logarithm of on the right side. Okay? Therefore, x is less than 81. So to write the solution set, SS here means the solution set, then it's equal to 0 to 81. Remember that the value of your x must be greater than 0. Okay? So we have the exclusion, the parentheses, okay, up to 81. 0 and 81 are not included. Okay? The value of your x must be in between 0 and 81. That's why we use the parentheses. Okay. Meaning 0 and 81 are not included in the solution set. So this one is the, what form is it? Is this? And then this one is the set builder. So we have the set of all x's such that x is an element of R and that x must be greater than 0 but less than. Okay, it should be less than 81. Okay, sorry for this. It's a typographical error. Okay, let's have the fourth one. Okay, so as you can see here, both are expressed as the logarithm to the base 2. Okay. And if you will check, must be greater than 0, then 3x must also be greater than 0. Solving for the x's, we have negative 3 halves and then greater than 0. Okay. So dropping out, it should be logarithm of 3x here. The 3x must be here. So dropping out the logarithm to the base 2, we have 2x plus 3 is greater than 3x. Okay, so solving for that, negative x is greater than negative 3. So the numerical coefficient of x here is negative 1. So our rule, if it will be divided by a negative numerical coefficient, then we have to reverse the symbol. So x is less than 3. Okay. So to check, diba? Since here, x is greater than negative 3 halves, then 3 is really greater than negative 3 halves. In this case, 3 is again greater than 0. So for the solution set, so 0 and 3 again are not part of the solution set. Therefore, writing that in set builder notation, the set of all x's such that x is an element of the set of real numbers, x is greater than 0 but less than 3. So all numbers in between 0 and 3 are part of the solution set of the given logarithmic inequality. So I hope you don't have questions on that. So let's have this one. So again, it's both expressed with the same base. So checking that. So the 3x here must be greater than 0. The 2x plus 3 must be greater than 0. And the 3x must be greater than 2x plus 3 as is stated on the properties of logarithm. Our b here is greater than 0 but less than 1. Okay, and then we have this one. Okay, so that's why it's the opposite in symbol. So x here is greater than 0, 2x is greater than negative 3, solving for the x's. Okay, so these are the possible. Okay, so that is the solution set. So how come it becomes like that? 3 up to infinity. X is greater than 0, x is greater than 3, up to greater than 3. We cannot include this, remember. Okay. Because if we will try to solve 3x is less than 2x plus 3, so we'll have x is less than 3. We need to reverse the symbol. Okay, let's have representation of logarithmic functions. So these are the objectives. So I hope you know how to convert logarithmic equation to exponential equation and vice versa. Represent logarithmic function through its table of values, graph, and equation. Then sketch the transformation of the graph of the logarithmic function. So this is the graph of a logarithmic function. This is what it looks like. If b is greater than 0, then it will be like this one. But if b is greater than 0 but less than 1, the base becomes fraction form or in fraction form. Then its graph will look like this one. Okay. So sketch the graph of y equals logarithm of x to the base 2. Okay. So if we will put some values or try to, how do you call that? Assume values of y's from negative 4 to 3, then solving the logarithm of this one, having that value, we will have negative 4 for this one equals the logarithm of x to the base 2. Then transforming that to exponential form, we have 2 raised to negative 4 equals 2x. Therefore, x is equal to 1 over 6. Okay, so doing the same thing from negative 3 to 3, then we will have this one. So these are the solutions. Okay. As you can see, as y increases, x also increases, diba? So this is the table of values of the given logarithmic function. Now let's try to have the domain range intercepts, zeros, and asymptotes of logarithmic functions. So you know already what a domain and range is. You have encountered intercepts, zeros, and asymptotes for the rational exponential functions, but you have to consider the following properties for the case of logarithmic function. That the domain is the set of all positive number. So x should be all positive. The range is the set of all positive, of course. It is one-to-one function, satisfies the horizontal line test. The x-intercept is automatic 1 and there is no y-intercept. The vertical asymptote is the line x equals to 0 and there is no horizontal asymptote. So automatic, no y-intercept, no horizontal asymptote. Okay, so look at the first example that we had. This is the table of values for the given logarithmic function y equals 2 times the logarithm of x to the base 2. Okay, this is another one, rather, because we have here the 2. Okay, so solving for that, ayan po, these are all the solutions on how to get the value of your x's. Okay, then let's try to, okay, the domain is automatic 0 up to infinity. The range is infinity to infinity. The vertical asymptote, finding x squared here, is equal to 0. Therefore, x is equal to 0, which is also the zeros of the given function. Okay, so the x-intercept, the logarithm of x squared to the base 2 is equal to 0. Then the x-intercept is 1, okay, denoted by 1, 0. Okay, okay, the zeros here, whatever is your x-intercept becomes the zeros of the given logarithmic function. Okay, let's try to solve one problem. COVID-19 pandemic. Actually, there is another application of logarithmic function. If you have, in terms of sounds, the decibel. Okay. So, but here we tried to integrate our current situation, which is the COVID-19 pandemic. Okay. So in this case, let us assume that the virus has an initial population of 10,000 and grows to 25,000 after 50 minutes. Assume that its growth follows an exponential model f of t is equal to a e raised to kt, representing the number of viruses after t minutes. The e is used in the model because the virus continuously grows over time. So it's somewhat under also of the exponential function. So find a and k, then use the model to determine the number of viruses after 6 hours. So if we will use f of 0, which is 10,000, and f of 50 is 25,000 given in the problem. So therefore, we need to solve for f of 0 is equal to a e k raised to 0. Therefore, a is equal to 10,000. Then if f is equal to 50, then we have 25,000 e raised to k times 50. So 25,000 e raised to 50 k, this one. So that is equal to 5 halves. And finding the logarithm, the natural logarithm of this one, finding the natural logarithm on the other side also, then that is approximately equal to 0.01832, meaning for your a, which is 10,000, and your k, which is equal to 0.01832, then it can be expressed in exponential model as f of t is equal to 10,000 e raised to 0.01832t. Okay, whatever is the time, or the time elapsed, you can solve actually for that. And we will use this in order for us to solve letter B. Yeah, substituting the value of t, which is 360 minutes. Okay, then the value of that is this. So after 6 hours, that's why it's 360 in terms of minutes. Therefore, the number of viruses after 6 hours will become 7,315,750. So it's really an example also of an exponential function. Okay, so I hope you have understand the lesson on the logarithmic function. So that's all for our week 8, quarter 1. So I hope you have learned something from me for the 8 weeks already. So I'll just see you on the second quarter. Thank you, everyone.